Have you ever tried to book a room in a hotel where the floors aren't numbered in order? That is exactly how an atom works. Imagine the nucleus is the hotel lobby. Electrons are the guests, and being lazy by nature, they always want the room closest to the lobby, the lowest energy state. But as we move up, the architecture gets weird. We aren't just stacking floors, we're dealing with complex 3D spaces called orbitals.
Now, forget planetary orbits. Electrons live in clouds of probability. The s orbital is the simplest room, a sphere. It's symmetrical. But look at what happens when we add energy. The p orbital transforms into a dumbbell shape, pointing along axes. And the d orbital? It blooms into a four-leaf clover. These shapes define where an electron is likely to be found, and more importantly, how they bond with others.
Aufbau is German for building up. Think of this as filling a glass with water. The bottom fills first. In the quantum world, electrons don't jump to the penthouse if the basement is empty. We visualize this as an energy ladder. Watch as the electrons trickle down, occupying the 1s level, then the 2s, ensuring the atom remains in its most stable ground state before venturing higher.
Here is the plot twist. You'd expect the third floor, shell 3, to be completely full before opening the fourth floor. Wrong. The 4s orbital actually has slightly lower energy than the 3d orbital due to its shape and penetration towards the nucleus. To remember this, chemists use the diagonal rule. Watch how the arrows cut through the grid. This path is the true roadmap of the periodic table.
Let's put this theory to work with iron. Atomic number 26. We fill the inner shells. That's the argon core. Then, following our diagonal rule, we fill the 4s orbital with 2 electrons. We have 6 electrons left. These don't go into 4p. They drop back down into the 3d subshell. This specific arrangement, with incomplete d orbitals, is exactly what gives iron its magnetic properties. The geometry of the atom dictates the destiny of the material.